Guten Morgen. Ich heiße Chris. Sag einfach zu meinem guten Freund Scott vom Nibiru 2016 Kanal. Haben Sie einen guten Tag, meinen Freunden und meinen Kost. Auf Wiedersehen. Hi, Boo. Got a new presentation for you. Ready? Okay, let's go ahead and get ready. Brown dwarf star system in the inner solar system. The evidence. Part 2 of Physicist's Thoughts. Let's go ahead and begin. And part 1 of this series on a brown dwarf star system in the solar system, I wrote about the fact that the sun is going dark twice a year, and that this requires that a star come very close to the sun. What's up, Bo? You thirsty? Super bunny. In this article, I analyzed stereo A images from March 2011 and showed that the object of interest and those images behave like a star with an extremely large magnetic field. We're calling them plasma loops. As it generated a large plasma loop type ejection. It's right here. Very much looks like a CME. The fact that the object had to have such a huge magnetic field was suggestive of the fact that it was the core of a once much larger star and therefore must probably be a brown dwarf star. It's the elephant in the room. Nobody wants to deal with this. Figure 1 shows an HI1-A image from March 3rd, 2011 at 4:09 of the object of interest, showing the large plasma loop it generates. Since Venus does not generate its own magnetic field, this object cannot be Venus. But the object is yet labeled Venus. So it suggests that the objects in Secchi images are being purposely mislabeled in order to hide the truth. Figure 1, HI1-A, visible light images provided by Secchi from March 3rd, 2011 at 4:09. A large plasma loop is seen coming off the object of interest. Figure 2 shows an HI1-A or -A SREM image of the same object. The object is clearly having a CME or coronal mass ejection, and since only stars are supposed to have these, this is yet another indication that the object may be a star. Figure 2, HI1-A SREM images provided by Secchi for March 22nd, 2011 at 5:29. The red arrow indicates a coronal mass ejection coming off the object of interest. Now, the SREM images cannot have lens flares in them because they are produced from the detection of high energy particles and not visible light. Only visible light images where a lens is used can have lens flares in them. These lens flares can be smaller or larger than the primary image. Lens flares are always less bright than the object and can be extremely useful, especially those that are larger than the object. Figure 3 shows an image where just such a lens flare appeared. The lens flare actually seems to be a secondary image of the brightest object in that image, and that the object has to be our object of interest. So the lens flare provides a lot of details about our object of interest. Figure 3, HI1-A visible light images provided by Secchi from March 21st, 2011 at 3:29. The red arrow indicates the presence of solar flaring activity visible on the lens flare, suggesting that the object producing the lens flare is actually a star. The yellow line indicates the axis of the object, which is inclined 20 degrees to the vertical, or to the sun's axis. The lens flare shows that the object of interest has solar flaring activity on its surface, which is another indication that it has to be a star. Also, the axis of this object indicated by the yellow line is inclined by 20 degrees with respect to the vertical, or the sun's axis of rotation. This may yet be an indication that the object does not move along the ecliptic, but may have an inclined orbit with respect to the ecliptic. Figure 4. HI1-A visible light images provided by Secchi from December 8, 2010 at 8:49. The object of interest, or the objects rather of interest, are labeled as Jupiter and Mercury. Now we will examine two objects in Secchi images from December of 2010. The two objects of interest are labeled as Jupiter and Mercury, as shown in figure 4 above. But since we know that they are mislabeling objects, is happening. To hide the truth, we will examine the objects carefully to see if they are indeed planets or if they are stars. Figure 5, HI1-A visible light images provided by Secchi from December 5th, 2010 at 8:09. A red arrow indicates the object on the left, which looks a lot like a brown dwarf star in figures 1 and 3. Figure 6, HI1-A SREM images from December 5th, 2010 at 12:49 and December 6th, 2010 at 4:09. The blue arrows indicate CMEs, coronal mass ejections coming off the object on the left. Figure 5 shows an HI1-A image from December 5th, 2010 at 8:09 with the same two objects appearing in figure 4. The object on the left, indicated by a red arrow, looks a lot like the object in figures 1 and 3 that has been shown to be a brown dwarf star. Figure 6 shows two HI1-A SREM images of the same object from December 5th and December 6th, 2010. In these images, the object on the left is having a CME, or coronal mass ejection. Planets can't do that. It has a black colored CME, indicating the ejection of protons to the left in the first images, and it has a white and gray CME on the right, indicating the ejection of heavy ions and electrons in the second image. The fact that the object is having CMEs is an indication it is a star and not a planet. Figure 7, HI1-A SREM image from December 7, 2010 at 4:49. Both of the objects in the image are having CMEs indicated by blue arrows. In figure 7, both objects are having CMEs indicated by blue arrows, which again suggests that they are both stars. Figure 8 shows the image on the left in HI1-A SREM images from December 7th and 8th, 2010. The object has dark CMEs to the left, indicated by red arrows, and white CMEs to the right, indicated by blue arrows. Figure 8, HI1-A SREM images on December 7th, 2010 at 2:09, 4:49, 10:09, 12:49, 15:29, 18:09, 20:49, and 3:29, and from March 8, 2010 at 5:29. The object having CME seems to be rotating. In the first 4 images in figure 8 above, the white ejection from the star seems to be getting closer to it. This is an indication the object is rotating. In the 5th image, both a white emission to the right and very close to the object as well, a dark ejection also very close to the object, are visible. They are indicated by blue and red arrows. In the 6th, first image in the lower row, the white ejection is just barely discernible, whilst the dark ejection becomes more discernible. In the next 3 images, only the dark emission is visible, but it seems to be increasingly further away from the object. And in the last image, only the white ejection is only seen once again. This shows that the object has two ejections at an angle which is less than 180 degrees to each other. One of the ejections is white, and the other is black, and it shows that the object is friggin' rotating. Now, since the object returns to the initial configuration shown in the first image in figure 8, in the last image we can estimate the object's period of rotation. In the first image in figure 8 is from December 7th at 2:09, and the last image is from December 8th, 5:29. This suggests that the object has a rotational period of about 27 hours. Now the sun's rotational period is 24.5 hours, so this object is rotating extremely fast. However, this is what we would expect the rotational period of a dense core brown dwarf star to be, as the size of the star decreases at the same time that it becomes denser. Its rotational period decreases as a result of conservation of angular momentum, so the star's fast rotational period is yet another indication that it is a brown dwarf star. Then the object appearing on the right in figure 7 also has ejections, but does not seem to be as active as the object on the left. Nevertheless, since they both have plasma ejections, they must both be stars, and since they are so close together, they are most probably part of a brown dwarf star system in the inner solar system, and therefore associated to the dark sun cycle. In other words, we now have evidence of two stars being in this star system. Figure 9, HI1-A images from December 5th at 8:09, December 6th at 20:09, December 8th at 4:09, December 9th at 12:09, December 10th at 20:09, December 12th at 12:09, December 14th at 4:09, December 15th at 9, and December 16th at 16:07, December 17th at 16:09, and December 20th at 9 minutes, all from 2010. Figure 9 shows the motion of two stars with respect to each other in the sun, which is to the right in all the images. We know that both objects have plasma ejections that planets don't have and are therefore stars. We have evidence that the object that is initially on the right in the images in figure 9 is a brown dwarf star. Since they are so close to each other, the two objects are most probably companion stars, and most of the same system, and therefore likely to be brown dwarf stars. The reason both objects are most probably both brown dwarf stars is that they are both small, as we would expect brown dwarf stars to be. Also, a brown dwarf star will drain another star in its vicinity until both are brown dwarf stars. This is the reason why our sun is getting less and less bright and obviously weakening. The presence of two brown dwarfs is having a draining effect on our star. Now, in figure 9, we see that the two stars approach each other and eventually pass each other, with the object that is initially on the right also moving up in the images with respect to the object that was initially on the left. This is clearly demonstrated in figure 10 below. The object that was initially on the right is indicated by red arrows, and the object that was initially on the left is indicated by yellow arrows. The fact that the object moves upwards suggests that it has an inclined orbit with respect to the ecliptic. The orbital inclination seems to be about 20 degrees, which is the same as the axis tilt in the star shown in figure 3, which is also likely to be the object that is initially to the left of the image and indicated by a yellow arrow. This also suggests that the two stars are part of the same star system. Figure 10, HI1-A images from December 6th at 20:09, December 15th at 09, and December 20th at 09, all from 2010. The red arrow indicates the star that is initially on the right, and the yellow arrow indicates that the star that is initially on the left. The star indicated by the red arrow seems to have an orbital inclination of about 20 degrees to the ecliptic. In conclusion, two brown dwarf stars appear in Secchi images. In December of 2010, these brown dwarf stars' close proximity to the sun indicates that they are both part of the brown dwarf star system, associated with the dark sun cycle. Thank you again for subscribing and watching. Take care and have a great day. Got a new presentation for you. Ready? Okay, let's go ahead and get ready to it. Brown dwarf star system in the inner solar system. The evidence. Part 2 of Physicist's Thoughts. Let's go ahead and begin. And part 1 of this series on a brown dwarf star system in the solar system, I wrote about the fact that the sun is going dark twice a year, and that this requires that a star come. Guten Morgen. Ich heiße Chris. Sag einfach zu meinem guten Freund Scott vom Nibiru 2016 Kanal. Haben Sie einen guten Tag, meinen Freunden und meinen Kotzt. Auf Wiedersehen. Hi, boo. Large plasma loop it generates. Since Venus does not generate its own magnetic field, this object cannot be Venus. But the object is yet labeled Venus. So it suggests that the objects in Secchi images are being purposely mislabeled in order to hide the truth. Figure 1, HI1-A, visible light images provided by Secchi from March 3rd, 2011 at 4:09. A large plasma loop is seen coming off the very close to the sun. What's up, boo? You thirsty? Super bunny. In this article, I analyzed stereo A images from March 2011 and showed that the object of interest and those images behave like a star with an extremely large magnetic field. We're calling them plasma loops. As it generated a large plasma loop type ejection. It's right here. Very much looks like a CME. The fact that the object had to have such a huge magnetic field was suggestive of the fact that it was the core of a once much larger star and therefore must probably be a brown dwarf star. It's the elephant in the room. Nobody wants to deal with this. Figure 1 shows an HI1-A image from March 3rd, 2011 at 4:09 of the object of interest, showing the